Right, yeah, welcome back again. All right, this time we want to proceed from where we stopped last time. We are looking at hyperparameter tuning, which we focus today on Bayesian optimization and Optuna. Right, so we want to quickly look at how we can implement these two methods in Python. The Bayesian optimization is a strategy for optimizing objective functions that are expensive to evaluate, such as training a machine learning model. It is especially useful in hyperparameter tuning, where the function is to be optimized is black box, which means there is no explicit formula, and it's costly to evaluate, such as a long training times, and the number of evaluations need to be minimized. So then we can bring in this. So for Optuna, it is an open source hyperparameter optimization framework built around the idea of define by run. So which means you define by running. It is designed for efficient parameter optimization. It is seamless integration with Python and machine learning frameworks such as PyTorch, TensorFlow, XGBoost, and so on, especially in neural network. So it is flexible and scalable. All right. So we are going to quickly look at the implementation by using the breast cancer dataset we have used before with SVM classifier. So with database, we load the dataset here. All right, as we have done before. So I don't need to show a printed copy of the dataset anymore. So I've already shown you the previous class. So some things are added here that are not there in the previous one. So let's move gradually now. Just see that our dataset, and we do a subscaling here. All right, standardized data set here using the scaling function. All right, so we run the Bayesian optimization with a Scikit-optimize. All right, so when we run this particular one, it gives us our result here, which means this Scikit-optimized result. Our best parameter is found in this one: C 0.43, degree 3, gamma 5.39, kernel is linear. All right, so we have our accuracy at 0.9737, and the time is 27.55 seconds. All right, so for Bayesian optimization with Optuma, we have for Optuna we have run this. We have our values here. Okay, we have best parameter is 0.11, gamma is 0.09, and the kernel is also linear, degree 2. Accuracy is 0.9825, and the time is 1.6 seconds. Also, it's very fast. So when we compare the performance here, we run performance, we see that the method for Bayesian search with cost by validation, we have accuracy of 0.97. The time is 27.55 seconds, and the best parameter is 0.4, best C 0.43. Again, it's linear, and for Optuna we have 0.9824, and we have time is 1.6 seconds. Then our best C is 0.11, and it's also linear. Graphical output for both performance, including like accuracy, training time, and parameter distributions, is plotted also. We'll look at it, just plot each of them one by one. Okay, by showcasing their distribution step by step. So you can save them here. You want to save them in your and open them later. So you can see this is the first one. All right. Let me just start from here. All right, this first one, we have a model accuracy comparison. So our model accuracy comparison is giving, you can see that we have our Optuna is giving us high value, and the base search is giving us this smaller one. So we have our training time here, which means based on it takes longer time to train, while Optuna training is within the very short time, very fast. Then we have our parameter combinations, where we have for polynomial, we have a RBF, we have a linear. You can see combining the parameters together in a network base. can see them here. So objective value C, can you see? So we also have Optuna optimization history, objective C. You can see for best value, you can see here. So best value is found here. Let's see. So now we also have a performance importance. We have kernel, we have a gamma, we have a C, and we have a degree. Okay, so these are just the charts we have for each of them. So the key visualization generated and interpretation of them. The first one is a accuracy comparison bar plot, which compares the test accuracy of both methods. Then another thing we have is a training time comparison bar plot, which shows the time efficiency for Optuna is typically faster. We also have Optuna parameter distributions, which is parallel coordinates, which reveals which parameter combinations led to high accuracy. And we also have Optuna optimization history, which tracks how accuracy improved over trials. So Optuna parameter importance also identifies which parameter most influenced accuracy, e.g., C, which is more than kernel. All right, so we can each graph or each plot for accuracy time plot, the higher bars are better for accuracy, lower bars are better for time. Okay, for parallel coordinates, follows lines to see successful parameter combinations. So for potential parameter history, we have steeper curves indicate faster convergence, and for parameter importance, focusing tuning effort on parameter with high importance. And the key difference is that from our feature, we have both of them. I mean, Scikit optimize and Optuna algorithm. For algorithm Gaussian process, for Scikit, we have Optima, we have a tree structure pattern estimator, and for parameter space, it requires a split is bound, while Optima requires dynamic search space. For parallelism, we have a built-in, which is a number of jobs is equal to 1 or -1 rather. So Optima requires distributed setup. Visualization is limited in Escape Optimize. Optima have advanced plot optimization history and early stopping manual callbacks in a Scikit Optimize, and a built-in, which is pruning for Optuna. But this is best for small, medium scale or medium space. That's for Scikit-learn. Optima is for large or complex space. All right, for practical implementation, we can choose a Scikit Optimize if we want a seamless integration with a Scikit-learn, or you want parameter space in small to medium, okay, 20 dimension, less than or equal to 20, and you want to out of the box parallelization. But you can choose a Optuna if you need advanced features for pruning and visualization, and you need parameter space. The parameter space is large or hierarchical, or you want to optimize non-Scikit-learn models. So in summary, Optima is faster for complex space due to a TPE algorithm, and Scikit Optimize integrates better with Scikit-learn pipelines. Both outperform grid and random search we see in our previous class in efficiency, if you remember. And for neural networks, Optima is generally preferred because of its high accuracy. Okay, so we conclude by we use a tree structure estimator, which is more sample. That is the reason why Optima is faster and more efficient. It also found a simpler solution like a linear kernel, which is faster than the Scikit-learn for RBF, and both achieve the same accuracy despite the different parameters actually. But Optuna is faster and more efficient, as we see in this particular plots and a comparison. So that is that for today. I will see you in the next class. We'll look at something very different. Thank you so much for listening. I will see you in the next class.